possible. So instead of going from left to right, we're going to go from right to left. So looking at this hexane 2-all, our subs on here, we only have this epoxide. And the way we're going to label that is 5,6 epoxy. And that's a little bit different than what you're used to with alkanes. Normally, you would just say like 5-ene, just to say that it starts on 5. This is different, and you want to specify both carbons. So we have 5,6 epoxy. Do we have any other substituents on here? Awesome. Are we set to go to name this thing? Are we missing anything? Stereochemistry. Yeah, we're provided stereochemistry. Anytime you see dashes and wedges, that's a huge red flag. Just always double check. So let's go ahead and look at carbon 2 first, just to keep that consistent. What we're going to do, we're going to assign priority to each atom connected to that carbon 2, where our stereochemical site is. Is that carbon chiral? Yes. If you have dashes and wedges, but the carbon isn't chiral, you don't need to do RNS stereochemistry. In this case, it is. And how do we know that it is? 4 distinct groups. Yeah, we have a hydrogen, an OH, a methyl group, and then the whole rest of the molecule. So 4 distinct groups connected to that thing. So we know we need to use RNS stereochemistry to specify which orientation it's in. So we're going to assign priority to everything connected to this, and that goes by atomic mass. So we're going to look at every atom connected to carbon 2, and we have an oxygen, a carbon, and a hydrogen. Which one's going to win? Oxygen. Oxygen's the heaviest. So we're going to give that our number 1. But we do have 2 carbons on here, so we're going to have to break a tie. We're going to look at carbon 1 here. What's connected to carbon 1? 3 H's. All right? How about carbon 3? We have a carbon and 2 hydrogens. And what we're going to do, we're going to look at the first point of difference. So this first hydrogen here, this first carbon, that's the first thing we see that's different. So which one's going to win here, carbon or hydrogen? Carbon wins. So does carbon 3 or carbon 1 win? Carbon 3. Yeah, we're going to pick this carbon 3 because it's connected to that extra carbon, while this carbon 1 is just connected to 3 hydrogens. So that's how we're going to go about breaking that tie. So we're going to go ahead and give that our number 2 priority. Then this other carbon will get our number 3. Then what do we look at? The hydrogen. Yeah, our 4th priority group. It may not be hydrogen in every single case, but we're going to look at our lowest priority group, which in this case is hydrogen. And what we want to do, we want to see whether it's in the front or in the back. Is it in the front or in the back? In the back, yeah, it's on dashes. Is that good or bad for us? It's good, yeah, it means we don't need to flip our answer at the end. The way you approach it, if that H were in front, you would go ahead and do the problem as normal, just ignore it, keep it in the back of your mind, and then at the very end, we would just flip our answer to the opposite answer. So what we're going to do now, we're going to just draw an arrow from 1 to 2 to 3. Just connect the dots. So that is a clockwise arrow. So is that R or S? R. And again, do we need to flip our answer? Nope, so that is it. We're done with that one. Are we ready? Carbon 5, yeah, look at that. We have more dashes and wedges, and looking at it, we see it's chiral, right? 4 distinct groups attached to that thing. Carbon, carbon, but a different carbon, oxygen, and hydrogen. So 4 distinct groups, we know it's chiral. We're going to go ahead and do stereochem here. So let's go ahead and start. Which one's going to win? First priority. Oxygen, just like before. What's that? And then we have to break the tie between 2 carbons again. So is carbon 6 or carbon 4 going to win? I see some puzzled looks. Let's go ahead and do it. So looking at carbon 6, what do we have connected to carbon 6? An oxygen, a hydrogen, and a hydrogen. And looking at carbon 4, what do we have? Carbon, hydrogen, hydrogen. So we're going to look at that first point of difference. Oxygen versus carbon, what's going to win? The oxygen, so carbon 6 is going to win. Our second priority here. which leaves carbon 4 for our third priority. So now we're going to look at our fourth priority group, in the front or in the back. It's in the front. What does that mean? We need to reverse our answer at the end. So we're going to just continue the problem as normal, but keep in mind that is in the front, and we're going to need to reverse our answer. So just like before, we're going to draw an arrow, 1 to 2 to 3, right? So that's a counterclockwise arrow. Is that R or S? That would be S. So a counterclockwise arrow is S, but we know because our hydrogen's in the front, we're going to reverse our answer. So it was S, and it became R, because that H is in the front. So both of these are R. All right, we have all of our subs, we have our parent, we have stereochemistry. Are we good to go? We're good to go, yep. Are we just going to do RR? When you have multiple, go ahead and specify the number, the carbon number that we're talking about. So in this case, we're going to say the second carbon is in the R configuration, and the fifth carbon is in the R configuration, right? If it were just one, what would you do? You could just say R. Yep, you could just say the letter because there's only one possible site you could be talking about. So in this case, we want to say both 2 and 5 are R. Awesome, we're going to go ahead and move on. Do we put a dash here now? Yes, anytime you go from letters to numbers, you want to put a dash. So we're going to go ahead and put our sub 5, 6 epoxy, hexan 2 all. Looks good to me. The only other thing, you can put this 2 in front of the hexane, so that would make it epoxy dash 2 hexanol. Either way is totally fine. I just prefer the second way, but no foul either way. Awesome. And again, if you have any questions, we have some people here helping out, so just raise your hand and someone will come by and help you out. Awesome, moving on. So looking at this, we see a couple double bonds, and we see an ether here. What did we say about the priority of ethers? Very low. So what's going to be our parent functional group here? The alkene. And yes, we have a diene. So this is going to be a diene. So what we're going to do, now that we've selected the parent functional group, we're going to find the longest carbon chain containing that group. And that definitely looks like the left side. If we did the right side, we would exclude our double bonds. So that one, the choice is pretty obvious. So we're going to go ahead and number this thing, and we're going to put these double bonds, our parent, on the lowest possible number. So we're going to number from the left or from the right? From the left. We want to give those the lowest possible numbers. So let's start here, 1. You could start either way. Those carbons are identical, so that's fine. 1, 2, 3, 4, 5, 6, 7. That's the longest chain containing both of those alkenes. So what's our parent name here? We have a 7-carbon molecule, hepta, I'm going to go ahead and say 2, 4, ene, diene. Yes, exactly. We're not going to say ene. We want to say there's 2 here. So this di tells you that there's 2 alkenes in the molecule. 2 and 4 tell you where they are. So see, we have one starting on carbon 2, starting on carbon 4. What do we need to keep in the back of our mind, stereochemistry-wise, when we look at double bonds? E and Z. Yeah, we need to double check if we need to do E and Z stereochemistry. So how do you know if you need to do E and Z stereochemistry? If you have distinct groups on either side, then you're going to have to do it. So for example, let's go ahead and look at the far left one here, the one that starts on carbon 2. Looking at the left side of that double bond, I already kind of drew a little line, cutting these in half. Looking at the left side, are those 2 distinct groups? No, yeah, we already said they're identical. So do we need to do E and Z here? No, automatically we just throw it out. That's the end of that. We don't need to worry about it. Looking at this next one that starts on carbon 4. Looking at the left side of that one, 2 distinct groups? Yes, the other one is a hydrogen that's hiding in line angle. Looking at the right, 2 distinct groups? Yes. So you have to answer yes both times. Both the left and the right have to have those distinct groups. So we know here we're going to have to do E and Z stereochemistry. Let's just go ahead and finish that up. How are we going to do this E and Z stereochemistry? Similar to RNS, we're going to use atomic mass, and we are going to decide, looking at the left and the right side, which group on either side is going to have the highest priority. So looking at the left side of this thing, we have a carbon here. I'm going to erase this forward, move it a little bit. And we have a hydrogen. So carbon or hydrogen, which one is going to win? Carbon, right? Yep. Hydrogen is really small. So that carbon right there is our higher priority functional group on the left side. So now shifting our attention to the right side, we have a carbon and a carbon. So we're tied, right? And we're going to break the tie exactly like we did before. Exact same thing. We're going to look at what it's attached to. In this case, we have a hydrogen, hydrogen, hydrogen. 3 hydrogens. Carbon 6, we have a carbon, hydrogen, hydrogen. Looking at that first point of difference, we're going to see that carbon 6 down here is going to be our higher priority carbon. So now what we're going to do, we're going to ditch that original half line that we drew. We're going to draw a new line across the length of the double bond. We're going to look across those sides. Are those high priority functional groups on the same side of the line or on opposite sides of the line? They're on opposite sides of the line. And turning that into E and Z, is that E or Z? That's E, yeah. Best way to remember it is Z is for the same side, So if they're on the same side, it's Z. And if they're on opposite sides, you're going to have E. So we know that we have E stereochemistry here because they're on opposite sides. Awesome, so we got that knocked out. Let's go ahead now and look at our subs. We'll do that in a different color. So we already took care of our diene in the parent name because that's our parent functional group. So are we going to consider those subs? Nope, we already labeled them in the parent, so we don't need to worry about that. So let's look at, we have a methyl group here and a methyl group here. So on carbon 2 and on carbon 5, we have methyl groups. Are we missing something there? Yes, dimethyl, right? Same thing before with diene. We want to say that there are 2 methyl groups. Dimethyl, right? Awesome. Moving on, this is our only other substituent, this thing out on the end. And the way we're going to name ethers as a substituent, we're going to look at the number of carbons. We have 2, so what is that? Methyl, ethyl, propyl, ethyl, yeah. And the way we're going to name this as a sub is ethoxy. It's an ethoxy substituent. And what carbon is it on? Carbon 7. Yep. So we're going to have 7 ethoxy. Awesome. Have we taken care of everything? Yes, we have. We're good to go. We have stereochemistry all figured out. We have the parent name and all the subs, all the numbers are right. We're good to put this thing together. So let's alphabetize this thing. Are we going to put this dimethyl here first? No, yeah. So you are going to alphabetize based on this M. Numeric prefixes don't count. So dimethyl, trimethyl, never alphabetize based on those. What are the prefixes that count? Yep, neo, iso, and cyclo. Those are the only one you need to remember. And you can remember Nick. So neo, iso, and cyclo are the only ones you need to worry about. You would alphabetize based on those. So you would alphabetize based on N, I, or C if that were shown. But any of the numeric prefixes like that, we're not going to worry about. So we're going to alphabetize these things using this M and this E. So which comes first, E or M? E. So we're going to go ahead and put that ethoxy as the first substituent. What do we put even before that? Yeah, we're going to put our stereochem. So are we going to say 4E? I would actually just say E. So if you have only one stereochemical site, you can just say E. And even though there are two double bonds, one of them has no stereochemistry. So it's not even possible for that to have an E or Z configuration. So you're not going to confuse anyone if you just write E. So in parentheses, we're just going to say E. And then we're just going to say 7-ethoxy. Are we missing anything there? A dash, right? We went from a letter to a number. So E. 7-ethoxy. We're going to go ahead and continue with our methyls. Dash. So 2, 5 dimethyl. Right? Running out of room here. And then we put in our parent. Dimethyl. Hepta. 2, 4 diene. Awesome, we're good to go. Again, you can put the 2,4 in front of that. So you can say 2,4-heptadiene. That's totally fine too. Awesome, good to go on number 2. Raise your hand if you have questions. Moving on to number 3. So, looking at this molecule, what is our parent functional group? Kind of tricky. So we have this ether here, which we know is low, and we have this bromine here, which we know is pretty low. Our parent is actually alkane. Alkane is the highest priority functional group here because both of these are going to act as subs. Remember when you named alkanes with halides on them? They always ended in ane, right? So the alkane is still the parent here. The alkane has the highest priority. So we're going to find the longest carbon chain containing that priority group, right? So in that case, it's just the longest continuous carbon chain. So we're going to look. We have 1, 2, 3, 4, 5, 6, 7, 8 on the left. 1, 2, 3, 4 on the right. That's a little tricky. You would be tempted to try to include all of this in the parent name because it looks like that's the most complicated thing going on and that the left side's just a straight chain alkane, whatever, we don't need to worry about it. That's a little tricky. So this left side is our parent because it's the longest carbon chain containing our parent. So we're going to number this trying to give substituents the lowest possible number. So we're going to number it so we have 1, 2, 3, 4 versus numbering from the left 1, 2, 3, 4, 5. So which wins, 4 or 5? 4, right. So we're going to number this from the bottom 1, 2, 3, 4, putting that ether on 4 instead of 5. So we got 4, 5, 6, 7, and 8. Awesome. So what's our parent name here? Octane. That's it. Nothing else. Octane. Y'all have seen that at gas stations, right? Awesome. So we have octane. Do we have any stereochemistry to worry about here? No. No dashes and wedges. Not even any chiral carbons. If there is a chiral carbon without dashes or wedges, do you need to worry about stereochem? No, you can't possibly figure it out. I mean, there's no way to know unless she tells you with the dashes and wedges which configuration it's in. So if there's no dashes and wedges, no need to worry about RNS. Yes, so Fisher projections, RNS is still fair game even though dashes and wedges aren't there because they're implied. Remember with Fisher projections, the dashes and wedges are implied. So remember with a Fisher projection, which would look like this, you can kind of remember it as little bow ties. So if you ever see a Fisher projection, which could show up on this exam, you want to remember that anything sticking out to the sides is on a wedge. In this case, no Fisher projection, so no stereochem. We're not worried about it. So how do we name this substituent? We have a 1, 2, 3, 4 carbon ether. So what's a 4 carbon substituent called? Butyl. And as an ether, it would be a butoxy substituent. And where is that butoxy substituent? It's on carbon 4. But notice we have this bromine out here. So we're going to have to use some complex substituent naming. This bromine could go anywhere. It could go out here on the furthest one, third one, second one, first one. We don't know that for sure. So we need to number this thing now to say where this bromine is going to go. So we're going to number at the first carbon connected to the parent chain. that means we're not going to call this oxygen 1. So normally you would go from just the first atom connected to the parent. That's not how we're going to name this. We're actually just going to go with the first carbon. So don't count that oxygen as 1. So we're going to call that 1, 2, 3, 4. Naming from the parent out. Awesome. So this 4-butoxy, we have something on it, and we're going to need to say where that is. So we have a 4, and we're going to open a parenthesis here. What that means is that we're going to say that there's something on this 4-butoxy, and that this 4 applies to the butoxy and not anything inside of it. So 4, open parenthesis, and then we have another 4, because this bromine is on carbon 4, so 4 bromo, correct? Awesome, so 4 bromo. So this whole complex name, the parentheses here tell you that the 4 inside the parentheses, oops. I'm going to put that at the end here. Sorry about that. So the 4 in here, 4 bromo, tells you that the bromine is on the 4th carbon of that butoxy substituent, right? So we have out of here carbon 1, 2, 3, 4. So the 4 applies to the butoxy. What does this 4 apply to? The one out in front of the parenthesis. Octane, right? So outside of the parenthesis, this 4 is going to apply to octane. Everybody see how that works? Awesome, cool. So inside applies to butoxy, outside applies to octane. Both are 4. So we have the parent, we have no stereochem to speak of, and we have all the subs done. So we're good to go with naming this thing. We have no stereochem again, so we're not going to start with it. We're just going to start with our subs. So 4 bromo, butoxy, octane. Awesome. Any questions? Raise your hands. People will come by. All right, facts. Looking good. So place the following anions in order of increasing stability. So just looking at these things, we already can see that there's going to be resonance here. So we have this negative charge that's going to be bouncing around between different atoms. So looking here, we have a negative charge on a carbon, negative charge on a carbon, negative charge on an oxygen. That's something to keep in mind. Where do we want negative charges here? Do we want them on oxygen or on carbon? Oxygen's best. But let's go ahead and look first at this first example here. So we have some resonance going on. This lone pair, these 2 electrons that are out here, can resonate here, kicking up this lone pair onto the oxygen, putting a negative charge here. Likewise, it can also go out here, kicking this pi bond up onto the oxygen, putting a negative charge here. So your whole resonance contributor is going to look something like this. Or the hybrid, I guess I should say, is going to look something like this, with a delocalized negative charge. And partial negative charges will be on this oxygen, and this carbon. So let's go ahead and compare that with the far right here. Here we have lone pairs, 3 of them out on this oxygen. One of them is going to come in here, kick up onto the oxygen. So our hybrid will look something like this. Oops. Partial double bond character, negative charge with partial negatives on each of the oxygens. So looking between the first and the third, let's just compare those first. We have delocalization across 3 atoms versus delocalization across 2. Which one do you think is going to win? So it's counterintuitive. Delocalization across 2 is going to win this time. The reason being, we don't like that negative charge on the carbon. Remember that from the beginning? And in order for that to resonate, in order for the charge to delocalize across both oxygens, it's going to have to pass through that negative carbon state for those to delocalize. And it really does not like to be on carbon. Carbanions are very unstable. So the interesting point here is that the quality of resonance contributors matters more than the quantity. Quality is best. So on the right here, we have delocalization across just 2 oxygens. How happy is oxygen with a negative charge? It's fairly happy. How happy is oxygen with a partial negative charge? Totally fine. No problem at all. So this, we just have partial negative charges on 2 oxygens, no problem at all. And we don't put any negative charges on carbon. So in this case, 3 is going to beat 1. We'll say that for now. Our third one is going to beat our first one. Looking in the middle here, we have another negative charge on a carbon, which we said was good or bad? Bad. We don't like that. We want them on oxygen. Looking here, is this going to pop out here? No, there's already 3 hydrogens on here, 3 more single bonds. That would have to kick out a hydrogen, and that's just not going to happen. A hydride won't leave like that. So it's not going to delocalize to the right. It's only going to resonate with the left side, kicking that up onto the oxygen, negative charge there. So now we have delocalization across 2 atoms, but they are carbon and oxygen. So looking at these first 2 here, which one is better, the left or the right? The left. Yep, both of them have a negative charge on the carbon, which isn't great, but the left does have more delocalization. So quality is very similar between these 2, and then quantity kicks in. So quantity here, 3 resonance versus 2 resonance contributors. Or I guess I should say delocalization across 3 atoms versus delocalization across 2. The 3 is going to win. So we know that our third one is better than our first one, and our first one is better than our second one. So we've solved the problem. Let's just put the numbers in. So this is our most stable, this is next, and this is last, dead last. If you have any questions on that, please raise your hand. The big takeaway from this is that quantity is not the most important thing. Quality is the most important thing, for sure. You want those negative charges on atoms that can handle it. 2 oxygens is great. All right, moving on. Place the compounds in order of reaction rate in an SN2 process. We sort of had a mantra last semester, just looking at this. What was it about SN2? No SN2 on sp2. So looking at these guys, we have our leaving groups here on that carbon, and that carbon. Are any of those sp2 hybridized? The middle there, look at the middle. Look at that carbon. How is that hybridized? sp2, right? How do you tell that? Talk to each other for 10 seconds. How do you know that's sp2? Ready, set, go. So I'm hearing some really good things. Biggest giveaway is the presence of this double bond right there, which is also called a what? A pi bond, because of the pi orbital that it uses up. What that means, in order for that pi bond to form, we need a free pi orbital, a free p orbital. So one of the p orbitals can't hybridize. And remember, we have an s, a p, a p, and a p. We have an s and 3 p's. And we know, because of that double bond, that we need at least one of them free to make that double bond, to make that pi bond, the p bond. So all we've got left are an s and 2 p's. Those will hybridize, giving you an sp2. That's just a quick orbital review. So looking at this middle compound, we have our leaving group on an sp2 carbon. And remember, we said no SN2 on sp2. Let's look at our question again. Place the compounds in order of reaction rate in an SN2 process. So how is none going to do here? It's definitely going to be our slowest. So we have 1 being the slowest, 3 being the fastest. If there's no SN2 reaction there at all, that's guaranteed to be our slowest. It's 0. The rate's 0. So looking at these other two, we have Br on a secondary carbon and a Br on a secondary carbon. How do we break this tie? Resonance. It's a little bit different than the resonance you're used to, but this double bond can stabilize the transition state while this reaction is happening. So what that means is that this first compound is going to have a faster reaction rate because of that stabilization from the double bond. It's going to stabilize the transition state. What does that mean about activation energy? Does that raise or lower the activation energy? It's going to lower the activation energy, right? You need less energy to get over that hump because you've got the stabilization from the double bond. You have a helper. So that's going to make the reaction proceed faster or slower? Faster, exactly. Lower activation energy means a faster reaction. So between the first and the third, which is fastest? The first, because it's got help. So 3 and 2. See that third one here is too far away from that double bond in order for that stabilization to happen. It's got to be right next door. All right, moving on. So, place the alcohols below in order of increasing reactivity in an acid-catalyzed dehydration. Sounds like big words. So let's turn this into something a little bit more manageable. Do we remember what an acid-catalyzed dehydration is? So the reagent, maybe to jog your memory, was H2SO4 and heat. And what's that going to do to that oxygen, or the OH? It'll protonate it, making it a good what? A good leaving group, and then it leaves. What kind of reaction happens if the leaving group just leaves? That's an SN1 reaction, remember? So in an SN2 reaction, bimolecular, the nucleophile has to be strong, and it's going to kick out that leaving group all in one fell swoop because the nucleophile is really strong and it can do that. In this case, in an SN1, unimolecular, the leaving group will just leave on its own. Then you'll have a positive charge, really good electrophile, so a weak nucleophile can come in and hit it. You don't need that super strong nucleophile this time. So this is SN1, or E1, either or. Because both of those have the leaving group leaving on its own. What's the rate limiting step in those reactions? The leaving group leaving. Yeah, and the generation of a carbocation. That's the limiting factor here. So what we're going to do, we're going to look at that carbocation here. We're going to go ahead and pretend that all of these have left. So let's go ahead and draw that. Got that positive charge out on a primary carbon. This one got a positive charge on a tertiary carbon. And in this one, we have a positive charge on a secondary carbon. What do we know about carbocation stability from Orgo 1? Do we want tertiary or primary? We want tertiary. Yeah, we want the highest number of substituents possible. So looking at these, do we have any that's tertiary? Yeah, so this middle one here, the leaving group will leave, giving us a tertiary carbocation. That's much better than if the leaving group left to give us secondary, if the leaving group left to give us secondary or primary. So our tertiary is going to win. Deciding between the next two, we have secondary and primary. Which one's better? Secondary. I'm going to go ahead and give that our 2. I'm going to go ahead and give that our 1. Awesome. If you have any questions on that, raise your hand. Just to clarify too, I mentioned SN1. This is an E1 reaction. What do you generate here? A double bond, right? So it's an elimination. It's sort of like E2 when you generate the double bond, same thing. In this case, you're going to generate that double bond, making it an elimination reaction. Sorry if that was a little confusing, but it'll follow like the SN1E1 general mechanism, but it will follow the elimination pathway. The rate limiting step, however, is the same for both. Either way, the rate limiting step is the leaving group leaving and the generation of that carbocation. Whichever gives you the most stable carbocation, that'll have the lowest activation energy, quickest, easiest reaction. Awesome. Let's keep rolling. Place the following compounds in order of increasing reactivity with NaOCH3, methoxide. So looking at this is kind of tricky. Which one's the odd man out? The first one. What is the first one? What functional group? We have an ether, and we have two epoxides. What do we know about ethers in general? Extremely unreactive. They're very, very stable. They don't react with really anything. There's kind of one exception. What is that exception? What's the exception? So what do ethers react with? Strong halo acids, HBr, HI. Remember that ether cleavage mechanism that you guys learned, chapter 14? That's the only reaction that ethers undergo. Other than that, they're extremely stable. Remember when you make Grignards, you use Mg and ether? You do that because ether is extremely stable, and it's not going to react with your Grignard. So we only know one reaction here. So ethers only react with one thing. And looking at our directions, so increasing reactivity with methoxide, is it going to react at all? No. Yeah, there's only one reaction with strong halo acids for that cleavage. And we don't have a strong halo acid. So no reaction at all. That means the left is automatically the least reactive. So looking at these two epoxides. Epoxide opening is what kind of reaction? So this we have a strong nucleophile here, and it's going to come in and open our epoxide. And what type of reaction is that when we open the epoxide? Like what archetype does it fall into? It's an SN2. So this OCH3 will come in, tack here, and kick out a leaving group. That follows our SN2 mechanism, right? So this is pure SN2 here. So what is the main hindering factor for SN2? Steric hindrance. Yeah, we want the most exposed group possible. So looking at the middle and the far right here, you can attack at both sides. We have here and here, here and here. In the middle, we have the greatest number of substituents possible. These are tertiary and in some ways quaternary if you consider the oxygen, but very substituted. Is that going to be good for an SN2 reaction? Not so great. Looking here, do we have a better option? Yes. So looking at this carbon on the left, we've got a much more exposed site for that SN2 reaction. So is the reaction going to happen faster on the right or the left one? The right, yeah. So the right is going to win here. The right is going to be our most reactive. Middle is going to be 2. So we just looked at ethers and epoxides. I want to take a second and go over that ether cleavage mechanism, the only reaction you need to know with ethers. We're going to go ahead and go over that mechanism right here. So let's just pick a simple ether, ethyl-ethyl ether. And we're going to go ahead and react this with HBr. Most commonly, you'll see this with HBr and HI. HCl isn't great because Cl is not that great of a nucleophile. It's fairly stable. But bromine ion, iodine, they're very large. They have a lot of polarizable electron density. What does that do to their nucleophilicity? increases it. So those are better nucleophiles. So we're going to go ahead and use those. So the very first thing that's going to happen here, we're going to activate this ether. And the way we're going to do that, one of the lone pairs on the oxygen is going to go grab a hydrogen, kicking this bond off onto the bromine, like we've seen a lot of times. What we're going to get from that is a positive charge on our oxygen. 3 bonds to the oxygen. See that there? And a single lone pair. What do we know? This is unrelated, kind of, but what do we know about this? Right here. Good leaving group? Yeah, maybe especially if I draw it like that. Great leaving group, right? So we're used to seeing that. This is very similar here. So we've got this positive oxygen. It's going to be a good leaving group from this side or from this side. So what's going to happen here? We've got a nucleophile and a good leaving group. So we're actually going to have an SN2 reaction, right? So we have Br, lone pairs, and come in and attack here and kick out our leaving group. Same SN2 we've seen 100 million times. So now on the left side, we've created a bond with Br. So we have 2 carbons and a Br. And now we have an alcohol. See this whole thing here on the right, left. Took the H with it, so now we have an alcohol. Ethanol, turn up. So here now, we're not done. This is going to go ahead and react again. It's going to grab another proton. Yes. Yeah, I mean, this is, just kind of a general. So oftentimes you'll see this with 2 equivalents. That's a good point. 2 equivalents or excess. Because you are going to go ahead and use 2 equivalents here. That's a good point. This is going to react again. So we're going to protonate our oxygen. Positive charge. And remember, good leaving group. Br is going to come in. And what kind of reaction is this? SN2. Kicking out our leaving group. So we end up now with a Br here. These are both the same in this case. It may not always work out that way. So you could even just slash that and put 2 equivalents of that as your answer. This will come up again in the reaction section. I just kind of wanted to go over a very broad, super basic mechanism that'll help us out later. The other thing I would actually like to cover right now is epoxide opening. So let's go ahead and do that as well. And for this, we're actually going to have to do 2 separate mechanisms. Why is that? The conditions actually change the outcome of the reaction here. So we can do this reaction in either acidic or basic conditions. So we'll see how that changes things. Let's go ahead and use that. And let's actually, for now, let's just do this. So looking at our reagents here, are we in basic conditions or acidic conditions? We're in basic conditions. Oftentimes you'll be given alcohols or deprotonated alcohols like alkoxides. And there's multiple ways they can present. This is the basic way. The way you know it's basic, this negative charge here, means there's a lack of protons in solution. Some of them are missing here, see? So we have our alcohol here with the protonated state, and then some of it is in the deprotonated state. How do we know, what do we know about the strength of that as a base? It's a very strong base, so if there were any protons in solution, it would go ahead and grab them. So this is basic. So we're in basic conditions here. And there's an acronym that's really useful for this. BLAM. This applies to epoxide opening. And it stands for basic, least, acidic, most. Sounds crazy. What this means, though, it tells you which carbon is going to be attacked. So looking at this epoxide here, on the left side, let me just get a different color. The left side is less substituted compared to the right side. The right side's got 2 methyl groups on it, the left side's got 1, so it's less substituted. Looking at our acronym here, basic, least, acidic, most, it's going to tell us where our nucleophile is going to attack. So in basic conditions, we're going to attack the least substituted carbon. So what's going to happen here? A lone pair from this oxygen is going to come up and attack the least substituted carbon. Are we good? Are we missing anything here for this step of the mechanism? We are missing something. So we created a bond here, and remember there is a hydrogen. If we don't kick a bond out, we'll make a carbon with 5 bonds, right? So something has to leave. A leaving group has to leave. It's going to be that guy. And that's going to open our epoxide. You'll see this called epoxide opening, and that is the opening. And what this is going to do, it's going to cause that oxygen to swing out onto the next carbon over. So your nucleophile will attack, and then you'll end up with the oxygen that was in the epoxide being on the next carbon over. That'll help us later. So what we end up with, we have our nucleophile, OCH3. That's what just formed a bond, remember? So looking at this OCH3, we drew an arrow to the epoxide, so we formed a bond to that left carbon. There's 1 methyl group still on there. Do we have that anymore? Our epoxide there anymore? No, remember we broke that bond. So with this arrow, we broke that bond and sent a lone pair out onto the oxygen. So that's not going to be there. It's going to swing out here, and it's going to be negatively charged. So there was no proton on it, no nothing. It picked up a pair of electrons, and remember electrons are negative, so we're going to have a negative charge up on that oxygen. And then 2 methyl groups still here. And that is an SN2 reaction. The next thing that happens here, this alkoxide that we just generated is going to come grab a proton, and in this case, it'll be from methanol. That kicks that bond out onto the oxygen. So you end up with this guy. Awesome. In the basic pathway, the very first step was a nucleophilic attack. We're going to go ahead and do the acidic pathway, and that's not how this is going to proceed. So keep in mind, you'll get something absolutely different. Go ahead and move this up and over here so we have more space. All right, so let's go ahead and do the same exact example here. And instead, we're going to use OH with H+. Now we're very clearly in acidic conditions. Literally the definition of an acid is H+, presence of protons. So if we're shown protons here, we're definitely in acidic conditions. So usually it'll be pretty clear when we're in acidic conditions. With alcohols like this, that's probably when it's least clear, and this is how it'll be presented. So in the basic conditions, you'll see that O- stabilized usually by sodium, and then methanol itself. In acidic conditions, you'll see that H+ there. So that's how you know this is in acidic conditions. So I said this was going to proceed differently, and what's going to happen here, we have lone pairs on this oxygen, and this is going to come and grab a proton from solution. That's different. So keep in mind, if you get this on your mechanism section, be very sure whether you're in basic or acidic conditions, because the mechanism proceeds completely differently. So what you end up with you have an epoxide, and now it's protonated. Positive charge here, right? So what that did, so that positive charge on the oxygen, does that make it an electron withdrawing group or an electron donating group? If it's got a positive charge, does it want electrons or is it trying to give them away? it wants electrons, right? So if it's positively charged, if it's more positive than normal, it wants something negative to balance itself out. So now, instead of attacking that least substituted site, this was just steric hindrance. So that least substituted site was just the freest, because in basic conditions, there's no protons. So looking over here now, though, with this positive charge, we're going to get a lot of electron donation by induction from the most substituted group. So there will be a lot of extra donation there, and that makes this carbon here, the more substituted carbon, more partially positive, because it's trying to give some of its electron density away to the oxygen to stabilize it, right? So that's going to make that more partially positive. Does that make it a better or worse electrophile? A better electrophile, right? So something that's more partially positive is a better electrophile. So that's going to change where our nucleophile will attack. So our nucleophile is now going to attack the most substituted side, which is a little bit backwards for SN2. But if you can't remember, just look back at your acronym here. So we're in acidic conditions now. So we're going to attack the most substituted carbon now. I only really went into that just in case you got it for your essay question, but that would be the reason why. So now what we've got here, CH3OH. We don't have O- in solution. Remember, we don't have CH3O- here because we're in acidic conditions. So our nucleophile is methanol in this case. It's a weak nucleophile, but now we have a more partially positive carbon. So it's going to happen here. One of the lone pairs from the oxygen is going to come attack at the most substituted site. Again, different from the basic pathway. So what that's going to do, that is going to, sorry, let me just erase that. Go ahead and move this too. That's going to kick that bond out onto the oxygen again. So what you end up with is this. Do we have an O- anymore? That's what we had in the basic pathway. No, so there's already a proton there. So when it leaves, when it gets opened and kicked off, it's already an alcohol. There's no protonation step necessary for that oxygen because it was already protonated, right? So when it got kicked out, it's happy and neutral again. It gained a pair of electrons, went from positive to neutral. So we're good there. Down here, though, OCH3, does that look right? That OCH3 there? What about that hydrogen? Did anything happen there mechanistically yet? Nothing yet. So we had our nucleophilic attack, kicking out the epoxide. Nothing to speak of about this proton yet. So that thing is still there, right? Another difference from the basic pathway. Is that the only thing we forgot? A positive charge. Yep, that's the other thing here. So we have a positive charge there. Notice all of the charges in the acidic pathway as well are positive. Looking at our basic pathway, we had a lot of negative charges. And that makes sense, but just keep that in mind. So let's go ahead and put on our other groups. 1-methyl, 2 methyls. So we need to deprotonate this thing, and we're just going to use methanol. It's going to come by with its lone pairs, grab that hydrogen, kick that bond off onto the oxygen. The oxygen was positive. It just picked up electrons, so what is it now? Neutral. We're good to go. So it was deprotonated, went back to neutral. So our final answer would be this guy. OCH3 with your OH up here. Awesome. These are very important mechanisms to master, both this ether cleavage and this epoxide opening. Epoxide opening is a little bit review, but it's a little more in-depth now. She expects a little more of you now. So very important to know both of these. They will be on your test, 100% guaranteed. All right, so let's go back to our facts section. Looking at number 5, so spectroscopy, multiplicity. This is tricky. This is review, but still very difficult. So let's go ahead and dig in. So let's go ahead and read the directions. Let's just make sure to read carefully. Answer the following questions for the molecule below and place the answers in the appropriate boxes. What is the theoretically predicted multiplicity of proton A? So we're given that here. Theoretically predicted for proton B. proton C, and then what is the multiplicity of the signal for carbon D in the proton-coupled C13 NMR? That's very important to keep in mind. So let's start from the top. Looking at HA, let's locate HA right here. So we're trying to find the multiplicity of HA, and what that means is how many peaks will be generated. So that's your multiplicity. So for example, if you had 3 peaks, your multiplicity would be 3. So looking at this, we're going to count the number of proton neighbors. So normally you would just say, okay, there's 2 here, 2 here, so 4 plus 1 is 5, right? So multiplicity is 5. Not quite. It's really tricky with things that don't have free rotation. So when these protons are in different environments, when it's restricted in its rotation, let's call this, there's already letters, so let's use triangle and square. So the triangle proton is in a different environment than the square proton. It's stuck in its position. So what that means, we're going to have to count it separately and put it in its own term for the n+1 rule. So looking at this, we have 1 type of proton, 2 types of proton, and then looking the other way next door, a 3rd type of proton. So we're actually going to have 3 n+1 terms, right? Because we have 3 distinct proton types adjacent to it. So looking here, there's one proton like this first one proton like this second one, and then 2 protons like that third one. So we're going to say 2 plus 1. That is going to equal the number of peaks, or your multiplicity. Take 10 seconds, explain to each other why I did this. It's tough to explain, so I might not be doing it justice. Take 10 seconds and do it. Ready, set, go. Awesome. So 5 more seconds-ish. If you have more questions about this, I encourage you to ask. Spectroscopy will show up on every exam from now to the end of organic. So the sooner you can master this, the more points you're going to save throughout the entire course. So it's very critical that you master spec. It's difficult. Practice. Talk to people. Work on it. Try things for yourself. Get it wrong and figure out why you got it wrong. That's a really big thing. So went ahead and did the math. So our multiplicity is 12 in this case. So for proton A, we're going to see 12 peaks. I'm going to go ahead and move this whole line over to here. Awesome. All right, so let's move on to HB. Let's go ahead and erase all that. So here's B. So we're going to look at all of the proton neighbors, and we're going to take into account if there are distinct types of proton neighbors. So looking to the right, do we have a proton there? No. You would if it were cyclohexane. If this were connected to a cyclohexane ring, you would. But in this case, it's a benzene ring, and this carbon already has 4 bonds. So there are no hidden hydrogens here in line angle. So it's already got its full 4 bonds. We're good to go. So nothing on the right. Look to the left. How many protons do we have? 1. So our n+1 rule tells us number of protons is 1 plus 1 would be 2. You get 2. You could also write doublet. That's fair too. But I just put 2. Makes it easier. All right, let's move on to HC. There's a lot going on here. I want you guys to do this one. take 30 seconds. Do this together. See what you get. We'll go through it anyway, but I want you to try this one. See what you think. You've got till 8:13. Sounds like a whole lot. Sounds like a whole lot. It is a lot, but it's not that many. But it's probably. I don't think it's. Yeah, I don't think it's possible, but I don't want to say it for sure is it, but I highly doubt it. Highly, highly doubt it. All right, so 8:13. I think we've got enough time here. Sorry, that was a little loud. Sorry, guys, I didn't mean to spook you. Let's go ahead and break into this one. It's tricky. So HC is connected to this carbon right here. And we're going to look at the neighbors. So remember, we have to count distinct proton neighbors separately, and we have to give them their own term. So looking at these, that's one distinct proton type. How about those? Yeah, so this methyl group here and this methyl group here, both of those methyl groups are identical. There's free rotation. These are exactly the same. So are we going to count those in separate terms for n+1? We're going to lump them all together. So that's one term. And how many is that? 6 plus 1, right? Looking the other way, next door, 2 protons, right? So 2 plus 1, that's 7 times 3, giving us 21. So you'll have 21 peaks there. That's a lot of peaks. 21. If you have questions on that, again, definitely dig in. It's tricky. All right, so now multiplicity of CD, carbon D. And this was for C13 NMR. And remember, looking at the directions, this was proton-coupled C13 NMR. So with proton-coupled C13 NMR, looking at carbon D, we are going to count the number of protons attached directly to that carbon, if it is proton-coupled. And we'll use the n+1 rule again. So on here, we have CH2. We'll have 2 plus 1, giving us a total of 3. Do we count the neighbors? No. So just the carbon itself. Any hydrogens on that carbon. If it were proton decoupled, what would your answer be? 1. No coupling. So those protons connected to the carbon wouldn't be splitting the signal. So it would just be 1. So proton decoupled, you don't need to worry about it. So usually she'll say proton coupled. But double check that she does. There are a few old exams where she says proton decoupled, and the answer is 1. Not necessarily always. We can get into it, but often proton coupled, 3. All right, reaction section. Here we go. It's a marathon. Let's roll. This is going to be a lot of Orgo 1 review, so let's get that done. So we have a vicinal dihalide, potassium hydroxide at 200 C. We have sodium and ammonia, and this is liquid. She might say that. And then MCPBA. So looking at this, we see some double bond reactions, maybe some triple bond reactions, just kind of looking at this in advance, kind of getting our heads in gear for what's about to come. Let's go ahead and start at the top. So we have any vicinal or geminal dihalides with potassium hydroxide at 200 Celsius. That's going to give us an alkyne, a triple bond. It's going to do an E2 reaction twice. So it'll be a double E2 reaction. Where is this triple bond going to go? Internal. So yeah, potassium hydroxide gives you an internal triple bond. So what that's going to look like, the double bonds will rearrange. They won't form here, right next to the BRs. A rearrangement will occur to give you an internal triple bond. I'll just even say H3C, CH3. That's super long. Let's not do that. CH3. So what if you wanted a terminal triple bond? What would you use instead? Yeah, NaNH2, sodium amide. For your terminal alkyne at the end. So just remember that those are kind of opposites of each other. Awesome. Now, sodium metal, NH3, liquid ammonia. That's going to solvate electrons. What we're going to get here is an alkene, a double bond. We're going to add 2 hydrogens to this thing. And is that going to be cis or trans? Are those hydrogens going to be on the same side or on different sides? It's going to be trans. What would the cis equivalent be? Yeah, so H2 and palladium? Not quite. H2 and palladium. So palladium by itself is a great catalyst, and it'll take it all the way back to an alkane. So double. So what we have to add here is barium sulfate, BaSO4, and the solvent would be quinoline. So yeah, this may be shortened to Lindlar's catalyst. So you could even say H2 and LC, or Lindlar's catalyst. So that's the opposite of this one. That's like kind of the pair here. And try to move this to a little bit more of a convenient location. Trying to figure out where to put them, make it easier. Cis. This gives you trans. Awesome. So we're going to have the hydrogens opposite each other, trans. So what that's going to look like, we'll have a double bond, and again, hydrogens opposite each other. CH3. Awesome. That's step 1, and that's step 2. All right, so we've got our double bond. MCPBA, what does that do? So it's going to form an epoxide here. One thing I wanted to note here is that other peroxy acids also work. So you may see like H3C, O3H. O3H is, so that would look like this. OH. Other peroxy acids also do this. So keep that in mind. She may give you some other compound instead of MCPBA. So just keep that in mind. MCPBA, though, is specifically this guy. So that's metachloroperoxybenzoic acid. So it's another peroxy acid. This one will give us our epoxide. So what we're going to do, the best way I think to draw epoxides is to just draw that first and do that all in line. I wouldn't do any of these here on wedges or dashes. Oh, also with talking, I know some of you are shushing, but I do encourage you to talk if you have questions. Just keep it to a whisper, but do talk to each other for sure. This is really difficult. So if you have questions for each other, definitely ask each other, but just keep it to a whisper so that anyone wanting to pay attention can. But first thing I would do, so for drawing those epoxides, I would keep them all in the plane. And then I can go ahead and put wedges and dashes on the sides. Awesome. So our CH3s that we need to add here, are they going to be on the same side or opposite sides? They're going to be trans, so on opposite sides to each other. And we can look here from our double bond. That's where we get this information. So if the double bond were cis, if the H's were on the same side, we would continue to put them on the same side, as in both on dashes or both on wedges. In this case, we have trans. So we're going to put them on opposite sides. So let's go ahead and put H3C, CH3, and protons. I think that's probably the simplest way to draw epoxides. Just kind of keeps it easier to keep the whole epoxide itself just in the plane of the page and to draw dashes and wedges around that. Probably the best way to do it. All right, this is an interesting reaction. This is a little bit new. This is chapter 14 material. So we have an alcohol, an alkyl halide on here. We also have a strong, bulky base, which usually kind of gets us in the E2 department, but let's keep looking at this. We have Grignard, and we have H2SO4 in heat, which is typically dehydration. So this first reaction, even though you're very used to tert butoxide doing E2, does something slightly different in this case. So normally, deprotonating alcohols, would this be strong enough? Not normally. It can deprotonate phenols, because that's slightly more acidic. It can deprotonate that. But it isn't normally going to just deprotonate a regular alcohol. In this case, though, it can for a little while. There would be like a rapid proton transfer. So what you're going to get as kind of an intermediate, you'll get this guy. CH2Br. With your O-. That wouldn't be your answer for this step. I'm just kind of showing this. Normally what would happen if you tried to do that? So if you deprotonated it with like an alkoxide, it would just go ahead and grab the proton back. So like there is going to be some rapid proton transfer. So it's not that it like completely doesn't work. It's just that it's going to go ahead and grab it back. In this case though, there's something a little bit easier for it to do. Because this Br here, this alkyl halide, it's right next door. So you have a great nucleophile next to a leaving group, and it's right next door. So what this is going to do instead of E2, so instead of doing all that or grabbing its proton back or any of that, it's actually just going to go ahead and attack here, kick out your Br, SN2 style. Notice that that CH2 is just right next door, so the O- doesn't have to do hardly anything. It literally just boop, kicks it out, like it just barely leads, has to hardly do anything. So that's what makes this work. Normally, you wouldn't use this to deprotonate alcohols. You would use sodium metal or something like that instead. But in this case, it does something a little bit different. So that's good to know. I'm going to go ahead and erase this. I'm going to put the product. So if we have that O- coming in, kicking out the Br, what do we form? We're going to form a 3-membered ring with oxygen as one of the members. What does that sound like to you? An epoxide, exactly, yes. So we're going to form an epoxide. That's unique. That's new. That's not something we're really used to. Normally, this is like automatic E2. So just keep that in your head, that this could show up. So we end up forming an epoxide here. Step 2, we have a Grignard. And remember, so we have one side of the epoxide that's much more substituted and one side that's much less substituted. So we're going to need to pay attention to the conditions, remember? Because the acidic and basic pathway, they're going to proceed differently, right? Remember we talked about that? So looking at Grignard, is Grignard basic or acidic? Basic. Grignard is a very strong base. Remember, if you put Grignard in with any acidic protons, it's just going to rip those off. It's just going to grab them, and it'll kind of ruin your Grignard. But that makes it a very strong base, right? Because it wants to grab those protons for itself. So Grignard is a very strong base. And remember, blam, right? So we're in basic conditions. Is this going to attack the least substituted side or the most substituted side? Least. Remember, basic, least. So we're in basic conditions. It'll attack the least substituted side. So our Grignard is going to attack here. That's going to kick this out as an O-. Following that, H3O plus will protonate it. What you end up with Would you guys like me to draw the mechanism on that a little bit? I kind of talked through it, but... Okay, yes. So I'll erase it when I'm done, but CH3, CH2, MgBr. The bond between the carbon and the Mg is your good nucleophile, remember from Grignard. And that's going to attack our least substituted side, because blam. And that's SN2. So that's going to kick out the oxygen and open the epoxide. So the oxygen will end up on the next carbon over. So what you end up with temporarily is this guy. And there were just 2 hydrogens here, but we added a 2-carbon chain. Remember, Grignard is a carbon-carbon bond forming reaction. So we added 2 carbons there. So you temporarily end up with that. Following it with H3O plus adds a proton. And that resolves your negative charge. So you end up with an alcohol. And notice that alcohol swung over to the next carbon over. Keep emphasizing that. It's really going to help in synthesis once we get there. But so you end up with this guy. That's the final product. I'm going to go ahead and erase all this extra stuff and just move this over. And that's step 2. All right. We have H2SO4 and heat. What did we talk about that being a minute ago? Yeah, up here. Acid catalyzed dehydration. So that's an E1. We're going to form a double bond here. So we're going to protonate our oxygen. It's going to leave. We'll have a carbocation, and then we'll eliminate. Where are we going to eliminate? We have 2 options that are methyls here. And then we have one that's secondary. So we have 2 primary options and 1 secondary option. Which one are we going to go with? Secondary, yeah. So it'll preferentially form that double bond on the more substituted side. The only exception is a quaternary carbon. Would you form a double bond in that case? No, it would have too many bonds. And you can't abstract like a methyl or something like that. It has to be a proton. So it caps at tertiary. So our tertiary is our best. Quaternary is like 0 reaction, no reaction. And then you would go to tertiary or secondary or whatever else. So in this case, it's primary versus secondary. And we said tertiary was best. So we're going to pick the secondary side. Our alcohol leaves. Remember, this is acid catalyzed dehydration. So a proton adds and it becomes water, leaves, dehydration. So 2 methyl groups, remember those aren't going to have the double bond. Our double bond will form towards the most substituted side. And then let me just make sure and count carbons. That's always a useful thing to do. Just double check that you get it right. So that was the epoxide. We added 2 carbons for Grignard. So then 1, 2, 3, and 4. So we're good to go. That's our final product here. And that's for step 3. Yeah, what's up?
If you can open the mechanism for this one, because a lot of people are asking about it. The first step.
Just that first step?
Yeah, like the deprotonation and how it forms the, negative.
Yeah, how it forms that. Yeah, so I think probably the best thing, go back in the video, I kind of explained it, and draw it out for yourself. So I did talk through how this proceeds. So instead of doing the E2, so you have the O minus. He was asking me to go over the mechanism for this first step. Would y'all like me to do that actually? Or like, because I know we kind of went over it. I just don't want to like waste anybody's time if they're good. Let's hit it. So what's going to happen here, looking at that very first step, this strong base, tert butoxide, is going to deprotonate our alcohol. Let me go ahead and add a new page. So we had OH, methyl, methyl, and then CH2Br, and tert butoxide. So normally E2. So tert butoxide usually is a dead giveaway for E2. In this case, what it'll do, actually, here's a good question. So can E2 even happen here? No. Yeah, so the requirements for E2. So in E2, you abstract a proton from the carbon adjacent to your leaving group. So our leaving group is here, the bromine. We're going to look at the carbon next door. So the carbon adjacent. Are there any protons that we can even extract there? On this carbon right here? Anybody? No. Yeah, thank you, loud and proud. No. So there are no protons there. So can we do an E2? No. That helps you. That does help you. So the way that problem was structured kind of helped you to not do E2. The other way you know is that this alcohol is next door to the bromine. It's on the carbon next door. So what will happen here, this terbutoxide is going to take a lone pair, grab that hydrogen, and that's going to kick this bond out onto the oxygen. Normally, deprotonation of alcohols, like with terbutoxide or something like that, isn't a great idea because, so you'll end up with this, Br, O minus, and it usually will just grab its proton back and just kind of no reaction. In this case, though, there's something else it can do that's a little easier than wandering around and then grabbing a proton when it finds one. On its own molecule, it doesn't even have to go anywhere, there's a great leaving group right next door. And this negative oxygen doesn't have to go very far at all to attack that primary alkyl halide in an SN2, right? And that's going to kick this bromine out. So you formed a bond from this oxygen, so from this oxygen to this carbon, you formed a bond there, which closed a ring. You have a three-membered ring that's a triangle, so you end up with this epoxide, and you've kicked the Br away. If you still have questions about that, definitely ask. Go over the video again. I'll leave this in here. That's just kind of the quick mechanism. All right, so we're close. We're almost done with reactions. Last one. So we have a double bond. It's in a ring. We have hot KMNO4, potassium permanganate, warm concentrated. We also have NaBH4 and ethyl alcohol. Starting from the top. So warm concentrated KMNO4. The conditions matter here. There is a reaction that happens with cold KMNO4, and we'll look at that. With this warm concentrated KMNO4, we're going to cleave our double bond. Very harsh conditions. It's just going to oxidize the crap out of it. So that cleavage is going to make a straight chain. Can you all see that? So if you cut the ring open, you're going to form a straight chain. So let's go ahead and count how many carbons are in that chain to figure out how we're going to draw the next structure. So we have 1, 2, 3, 4, 5, 6, 7 carbons. I'm going to go ahead and draw 1, 2, 3, 4, 5, 6, 7 carbons. So let's just call this carbon 1. It's not like a nomenclature thing, but let's just say that's 1. So where you cut your double bond is going to be oxidized. And so on carbon 2, so to speak, we're going to have a carbonyl, and that's a ketone. So moving down 3, 4, 5, 6, 7, all the way at the end, we'll have a carbonyl there. Is it just going to stop at the aldehyde? No. Again, oxidize the crap out of it. KMNO4 is very strong. So this is going to oxidize it all the way to a carboxylic acid. That happened because it was terminal. Can you oxidize a ketone? No. It's stuck there. So if it's a ketone and it has carbons on either side, you can't make more bonds to oxygen. It's already got 4 bonds to oxygen. There's no hydrogens you can kick out. So it didn't happen on the left. You got a ketone on the left. But since you have this terminal one, that's how you end up with the acid. Awesome. So now we have this 7-carbon molecule with a ketone and an acid. And now we have NaBH4, which we know is a reducing agent, right? And now this is kind of where it gets tricky. What does NaBH4 reduce again? Just ketones and aldehydes. It's our weaker reducing agent, right? What would you do? So if you wanted to reduce everything, what would you use? LiAlH4, lithium aluminum tetrahydride instead. That's your much stronger reducing agent, and that reduces pretty much everything. So in that case, we would go ahead and reduce the acid. But since we said NaBH4 only reduces aldehydes and ketones, we're only going to reduce that ketone there. We're not going to touch the acid. Points off if you reduce the acid. So that was product of step 1. Product of step 2 gets us, what is going to reduce it to? Where does it stop? An alcohol. Right. Yep. We'll add a hydrogen to either side, to the oxygen and to the carbon. So you end up with the alcohol. So there's 1, 2, 3, 4, 5, 6, 7 carbons, and our acid is not touched by NaBH4. Not strong enough to reduce the acid. So I mentioned earlier, so this warm concentrated KMnO4 cleaves double bonds. What happens if it's cold? What if you use cold KMnO4? You would form a syn diol. Yes. So what you would get instead if you had cold, let's say, so cold gives you this. So let's put the CH3 dash. So you would form a syn diol. With the OHs on the same side, that's what the syn means. So OHs are both on dashes or both on wedges or whatever. So you end up with this syn diol, and the double bond goes away. But that's just for cold KMnO4. So warm concentrated KMnO4, that's the really harsh conditions. That's going to go ahead and cleave your double bond. So just keep in mind that the conditions matter on that one. And then again, remember, NaBH4 is kind of partners with LiAlH4. NaBH4 is weaker, LiAlH4 is stronger. All right, we finished the reaction section. Praise. No, we did not. We're halfway through. Let's keep moving, ladies and gentlemen. I'm sorry. So let's keep moving. All right, so this is great, actually. I'm glad this problem is here. I'm glad we're not done because I wanted to get to this problem. So we have an ether with HI. Remember, that's our only reaction with ethers. That's the only thing we need to know here. So remember, first step, this grabs a proton. I'm going to go ahead and do the mechanism on this one. So first step, lone pairs here, grab a proton, kicks off onto HI. You kind of want to show that in a little more detail, but whatever. You end up here. That's shorthand for benzene. Everybody good with that? The circle just means it's a benzene ring. So you end up with the O, protonated, positive charge, ether. So then our iodine, negative charge, good nucleophile, comes in and attacks here and kicks this out, right? That was what we said. Does anybody have a problem with that? You should. There's something wrong. This is an SN2 reaction, remember? And what did we say about SN2? No SN2 on sp2. That's critical. This is very likely to show up on your test. She will put an sp2 carbon in there. Very likely. So just pay attention to that. There is no attack there. So the iodine can't come in and attack at that benzene ring. And it's a little better illustrated here without the abbreviation with the double bonds. That's an sp2 carbon, right? No SN2 on sp2. That's very critical. So that does not happen. Bad. Don't do that. So instead, this is going to come in and attack here, kicking that out here. So no reaction happens on the left. So what does that mean? Does it just stays an alcohol, right? Nothing can react. So it's just going to leave it as an alcohol. So I'm going to go ahead and erase this. What you end up with, an alcohol on one side because there was no reaction, because it was sp2 hybridized, remember? So no reaction there. But on the other side, we have 1, 2, 3 carbons. So 1, 2, 3 carbons, iodine here. So the iodine will come in and kick out on the right. Because looking on this side, we have an sp3. Reaction's good to go. SN2 can happen on sp3 carbons, so we're good. What if she gave you something like this? No reaction. Nothing would happen here. Make sense? No reaction can happen there. No reaction can happen there. Both are sp2. So you would say no reaction for that step if she put that, which could be a creative way to test this. So that could show up. All right, so we've got our OH and the I. So I added to one side, not the other. All right, so now terbutoxide, and look at that. So we have our OH here and we have our I here. That looks a whole lot like this guy, right? It's different. This time, E2. E2 will happen here. And the reason is this OH is too far away. So that really only happens when it's next door. So in this case, it's just going to go ahead and do an E2. Likewise, look here. On the carbon next door to the iodine, next door to the leaving group, there are protons. So there is a good E2 site right there. So two things here pointing to E2 instead of the epoxide formation or the ether formation. So E2 will happen there instead. The other thing to note, tert butoxide is a strong base, and we said it wasn't really usually strong enough to deprotonate alcohols. Is it strong enough to deprotonate this alcohol? It is strong enough to deprotonate this alcohol. And this is one to keep in mind, especially for later. Going into test 2, it's really going to be important. That's phenol. And that proton is especially acidic because it's resonance stabilized with the ring. So an alkoxide, like tert butoxide, can come and deprotonate this. So that's also good to keep in mind. So what you end up with, see here, excess. You're going to end up deprotonating your alkoxide, right? Because it's phenol, resonance stabilized. And 1, 2, 3 carbons. And an E2 reaction happening here. That's a tricky one. Do you notice the differences between this one and the last one where we didn't do E2? In this reaction, E2 wasn't possible, for starters. Second thing is that the O- was right there, super close, and it can just go ahead and do that reaction right away. In this case, here, O- is far away, A, and B, E2 is possible. So those are two things that definitely point you towards E2. I think it's coming off. Hold on. All right. So we end up having two reactions here. Now, step 3, we have CH3Br. Notice here a primary alkyl halide. So this is a standard reaction, actually. So if you have an alkoxide and a primary alkyl halide, what will happen? Williamson ether synthesis. Those are the ingredients for Williamson ether synthesis. It must be primary. That's very important. It must be a primary alkyl halide. If it were secondary, what would happen? E2. Yeah, so you have a strong base, secondary alkyl halide, E2. So in this case, primary alkyl halide with an alkoxide, that is going to be an SN2. And that's going to be a Williamson ether synthesis. So this O- is going to come in and attack this carbon, kicking out the bromine SN2 style. And that is the Williamson ether synthesis. That's a technique that you should definitely have in your back pocket. So our final product, the Br left. And remember, Williamson ether synthesis, we're forming an ether. Because that O- came and kicked out the primary alkyl halide. Williamson ether. 1, 2, 3 carbons, double bond, nothing happened to that. And that's it for step 3. Step 2. Moving on, definitely raise your hand and ask questions, but I want to keep moving because I know it's taking a minute to do this reaction section. All right, so we have an epoxide here, and looking at step 1, what kind of conditions are we in? Acidic conditions. See this H+? That's a dead giveaway, acidic conditions. So first thing that'll happen, this will get protonated, and are you going to then attack the least substituted side or the most substituted side? Most. Remember BLAM. That's big. So basic least, acidic most. So we're in acidic conditions. We're going to attack the most substituted carbon. So what that means, our nucleophile is going to come in and attack the most substituted side. Acidic most. So that's going to add there. And that's going to kick the epoxide out onto the right carbon. If you're curious about the mechanism, go back and look at the other stuff we did, the mechanism I showed you earlier. But what you'll get, this will kick out, so you end up with OH eventually up here, CH3, H, 2 CH3s, and then O, CH2, CH3. That was your nucleophile that came in and kicked out, opened the epoxide. So that's product of step 1. Step 2, dichromate. What does that do? Yes, it's a very strong oxidizing agent. It's going to oxidize everything, essentially, that can be oxidized. Is it going to do anything to the ether? Nothing to the ether. Remember, one reaction. Only one reaction. HBrHI. That's it. Strong halo acids. So nothing else reacts with ethers. So nothing will happen to the ether. What about this alcohol, though? Yes, something definitely will happen there. Notice, is it primary, secondary? Is it at the end? Secondary. So are we going to form an aldehyde or a ketone? Ketone. Yes. OCH2CH3. Ketone. CH3. So this was our strong oxidizing agent. Oxidize the alcohol to a ketone. If it were terminal, what would you get? A carboxylic acid. Yes. It would first oxidize it to an aldehyde and then keep going. It would then oxidize it to a carboxylic acid. That is one thing to keep in mind too. I think the reaction sheet just has it going from the alcohol straight to the carboxylic acid. Keep in mind that the aldehyde is an intermediate step. So it goes to aldehyde first, then carboxylic acid. But what that means is that aldehydes are equally reactive in things like Jones and dichromate. So if you get an aldehyde and put in Jones, also goes to a carboxylic acid. So just keep that in mind too. That's an intermediate step. So first to aldehyde, then to carboxylic acid. All right, step 3, acetylide anion. This is a lot of review. Stay with me, guys. This was the other method that we used to form carbon-carbon bonds, right? What's the main method, our primary one, is Grignard. That's the one we're going to use probably most. But acetylide anion is another useful way of forming carbon-carbon bonds because you've created a really good carbon nucleophile. It helps a lot. Both Grignard and acetylide anion, that's the goal. You want to create a good carbon nucleophile. So what this nucleophile is going to do is going to come and backside attack our carbonyl. So what you'll end up with, I'll just say, so temporarily, OCH2CH3. I'm going to draw that the other direction. Oh, sorry, guys. How long does this possibly take? Sorry. Oh, here we go. And then O minus up here. So this acetylide anion is going to come in and backside attack the carbonyl, kicking one of those pi bonds out onto the oxygen. So you end up with that O minus. The oxygen gained electrons, so now it's negative. We still have our methyl because it was a ketone. Now attached, though, we have that acetylide, CH3. And that's just temporary because, see, look what's at the end of step 3 here. Then H3O plus. So this O minus here with its protons, or with its lone pairs, sorry about that, will come and grab a proton. So what you'll end up with, let's do line angle 2 carbons, and alcohol, C triple bond C, CH3. There's a lot thrown into one problem on that one. It's a good one. A lot of Orgo 1 review. All right, this is a very critical concept. So this is kinetic and thermodynamic control. I want to go to a little bit more of a basic example than this. So let's just look at this. So let's react this with HBr. Notice we have a conjugated diene. What that means is that these two double bonds are next to each other, and there is a continuous line of p orbitals. What that allows those electrons to do is to delocalize. So it's really going to look something like that. So it's just delocalized density across this whole thing. It's conjugated, is what they would call that. So, whoops. So the very first thing that's going to happen, remember when HBr adds to double bonds, the double bond to the nucleophile comes out and grabs a hydrogen, kicks those off onto the Br. So looking at this, we just grabbed from the double bond. We have a carbon on the left, carbon on the right. Which one is going to get the hydrogen? The left or the right? The right is going to get the hydrogen. Let's look at that. So we have the right that got the hydrogen, and the left got the carbocation. Two things are good about this. First thing is that the carbocation is secondary. If you had done it the other way, the carbocation would be primary. So that alone should tell you where it goes. Additionally, though, and this is the critical piece, is that now this thing can resonate. It's resonance stabilized carbocation, which is kind of new. And that gives this thing some interesting properties. So it is now going to resonate back and forth here. So I'm going to go ahead and draw that a little nicer over here. Double bond moves here. So you have two resonance contributors. Which one's more stable looking at these? We have the left or the right? The left is more stable, and you know that looking at this carbocation. That's the most unstable thing here, and you want to put that carbocation in the most stable place. So looking at the transition state, this left one, where the carbocation is secondary, is going to be best. So that's the most stable transition state. Let's just go ahead and finish the reaction with the left side. So in this case, Br minus with its lone pairs would come in. Let's do this one. Attack your carbocation. You end up with this guy. Let's pretend we wanted to use the other one. Instead, you would end up with this. The Br attacking the other carbocation. Looking at the products now, which one is more stable? This one depends on the double bond. So what do we know about alkene stability? Do we want more subs or less subs? We want more subs. So the most substituted alkene is the most stable. So we want something like that. That's the most stable. Would be tetrasubstituted. So looking between the left and the right, which one is better? The right. Yeah, so looking at the products, the right is better. Looking at the transition state, the left is better. So how do we decide what to do? You will be given one additional piece of information, the temperature. Let's assume we're at 0 degrees Celsius, low temperature. That means low energy. So if you're at 0 degrees Celsius, you don't have very much energy. So during the reaction, during that transition state, if you don't have very much energy, are you going to go to the more stable transition state or the less stable transition state? More stable. You don't have very much energy, so you have to do the most stable thing you can. You don't have any extra energy. So you have to stick with the left side because that's the more stable one. You don't have any option because you don't have any extra energy to spare. So that means that you will proceed the left pathway. So at 0 degrees, you would get this product. Let's say instead, let's put this over here. So 0 degrees. And let's say instead you were at, say, 60 degrees Celsius. Pretty hot, right? If you have lots and lots of extra energy, you actually can overcome the fact that this transition state isn't great to get to the better final product. So even though the transition state for this right pathway isn't awesome, if you have tons and tons of extra energy, you can overcome that to get to the best product. And so the left side we call the kinetic product, and then the right side we call the thermodynamic product. So kinetic is low temp or high temp? Low temp. And is that going to proceed with the most stable product or the most stable transition state? transition state. So if you have low temp, go for the most stable transition state. High temp, is that thermodynamic or kinetic? That's thermodynamic. And so then are you going to go with the most stable transition or the most stable product? The most stable product, yep, because you can overcome that bad transition state. That's a very critical topic for this test. It will show up. So knowing the ins and outs of this would be good. She may ask you for the boxes. She may put kinetic thermodynamic. That's possible. She may also say major and minor. What does major and minor depend on in this case? The temperature. So if you're given 0, what will you put in the major box? Kinetic or thermodynamic? Kinetic. Exactly. I think we're good. It sounds like you guys are understanding this, so that's great. Looking at this, NBS in light. Very first thing that happens, we have a bromine radical. That's going to come abstract a proton from a carbon adjacent to your double bond. So, and that's going to come from the most substituted one. Looking here at that carbon that I highlighted, are we going to abstract a proton from there? We can't. There's none. There is none. So even though we wanted the most substituted, we're still abstracting a proton. So since there's no proton there, we can't abstract a proton that isn't there. So we have to look at the others. So there's one and there's one. Those are our other options. Between a secondary and a primary, where are we going to take it from? The secondary. So we're going to rip a proton off of here. What that's going to give us is this transition state. I highly, highly recommend that you guys go ahead and draw these to help you. It's very difficult to eyeball these problems. Don't do it. Just go ahead and draw the resonance structures. Helps immensely. So the way this is going to resonate, I'm not going to do the single-sided arrow pushing because it's a little ridiculous and you don't even really need to. That double one's going to come over here. Let's go ahead and redo. That radical's going to be there. Missing a methyl. There we go. So notice, where the radical is where the Br is going to add. So where the second Br radical is going to add. So in one case, Br adds here, and then in the other case, Br adds here. Looking at radical stability, though, is tertiary best, secondary best, first, primary? What's best for radicals? We want tertiary. Yep, it's just like carbocations. So we want tertiary. Looking at the left and the right, which one is the most stable intermediate? The right. Yep, the right puts that radical on a tertiary site. That's best. Look at the temp, 0 degrees, right? Which one are we going to use to finish this reaction, the left or the right? We're going to use the right because it's the most stable transition state. Remember, at 0 degrees, low energy, we have no choice but to go with the most stable transition state. So our major product will be the kinetic product, and that's going to look like this. With the double bond di substituted. Our minor product will be the other. Let me get that out of the way too. Minor product will be the other, where our double bond is tri-substituted, which is great, but it meant we had to go through that bad transition state, and we didn't have the energy to do it. So that's our minor product in this case. That will vary depending on temperature. So seemingly simple on the surface, a lot going on under the hood. Definitely recommend learning that. That will be on the test. Moving on, we made it out of the reaction section. Mechanism. So we see some epoxides here, and we see a nucleophile, right? And remember, we have to pay attention to the conditions. Are these basic or acidic conditions? Basic, right? So we have that negative charge on the oxygen. So we're in basic conditions. Are we going to attack the least or most substituted side? The least. Blam. Basic least, right? Look at our product too. So we have a CH3O- as our nucleophile. And anytime that opens an epoxide, it's going to add to our molecule as an ether. So looking at our final product, how many times is that first reagent going to attack? Look at our final product. Once. It only is going to add once. Do you see that? So this CH3O- will add to the molecule when it reacts. So look at your product and you can see it's only going to add one time for this mechanism in particular. And you get that from your final product. And it looks like it's the one on the right. So let's actually go ahead and start our mechanism here. CH3O minus. Lone pairs here. And let's go ahead and attack the one on the right in the least substitute spot. That's going to kick that bond out onto the oxygen, open our epoxide. So go ahead and redraw. We added OCH3. There's now an O minus out up here. Methyl group still there. Methyl group still there. Epoxide still there. So now we're actually done with this CH3O minus, right? Because we saw it only added one time. So there's nothing else that thing is going to do, because if it were to react again, you would see two OCH3s, right? Does that make sense? Sweet. So now instead, we have a different O minus that we can work with. So what this is going to do is that right here, that O minus, is that a base or an acid? It's a base. We're still in basic condition. So is that going to attack the least or most substituted side? The least. So that's going to come over here, intramolecular attack, and it'll attack the least substituted side. And that is how you form your ether here. That's how that ring forms. That's how that ether forms. So one more thing we forgot. Did we forget anything here on this arrow pushing? Don't forget to kick out your epoxide. You have to open it, right? Don't forget that. That's critical. So we formed our ether, and now I'm going to go ahead and use the way they drew the product to draw this. So I'm going to go ahead and just kind of copy what they've got. So that ring just formed. So we formed our ether. Our OCH3 already added. Methyl group, right? But now let's go ahead and look at what we've got left. So there's a methyl group down here, right? And now we have an O minus that just got kicked out, right? And that was this guy. So that guy picked up a pair of electrons, so it's now negative, right? So then our step 2 comes in, H3O plus. There's no more reaction here because we've essentially got the right structure. We're basically at the end. Very short mechanism. Lone pairs here, H, O, H2, positive charge on that oxygen. Make sure to show that positive charge, because remember, show all intermediates, all formal charges. So show that positive charge and show that negative charge. So that's going to come grab a proton, kick it out on the oxygen, final product. Short mechanism, but complicated mechanism. Keep in mind, so that OCH3, you can see how many times your nucleophile will add, just looking at the product. So we saw it only added once, and we knew we needed to make an ether. So that intramolecular attack forms that cyclic ether. We'll do another similar mechanism like that tomorrow, and that might help clear some things up too. Let's move on to synthesis. This is my favorite part of the test. I love synthesis. So looking at this, we get cyclohexanol. That's important. Look at this, cyclohexanol, not cyclohexane. That's very important. So don't go back to cyclohexane and then, oh yeah, I'm done. Points off if you do that. You can't start with cyclohexane. You have to start with cyclohexanol. Cyclohexanol is actually really convenient because looking at this, that's great. I mean, that makes it really easy to just add that. So are we in a position to add that though? Are we ready to do that? What functional group might be better for us to work with in that case? It might be good to get back to an alcohol. In almost every case, it's great to get back to an alcohol because then you can use Grignard. You can use acetylide anion. You can use whatever you need to use to form carbon-carbon bonds because we have to break this thing down. So what reagent are we going to use to get an alcohol? You could use PCC or Jones. In this case, it's a secondary carbon, and it does not matter which one you use. It only matters if it's primary. So let's go ahead and draw this. OH. 1, 2, 3, 4. O. Right there. So PCC or Jones works. So let's just say PCC. in this case, so this is the case where it matters. So a primary alcohol is where there's a difference. If you use PCC on a primary alcohol, what do you get? An aldehyde. PCC is weaker and stops, remember? Jones, very strong, or dichromate, or whatever you want to use, is very strong. That'll take it all the way to the carboxylic acid. So primary is where it matters. Secondary here, this ketone, you can use PCC or Jones to get that ketone. Go ahead and erase that. That's when that matters. Quick review. So now we've got an alcohol. Now we've got something good to work with. And I know Dr. Bean has covered this. I know we talked about it last semester too. We see that our nucleophile is adding to that carbon. Where is the alcohol relative to that carbon? It's one carbon next door. Notice. What that means is that this was originally an epoxide. If instead you had this, where the OH was here, 5 bonds. Pretend that chain isn't there. So if it was something like this, instead, where your nucleophile is adding to this carbon and the OH is attached directly there, that would have come from a carbonyl. So an aldehyde or a ketone. So that in that way, you can figure out what was there before. So on our molecule, how the OH is one carbon over, we know that that attacked an epoxide and opened it so that the OH kicked over to the next carbon over. So this originally was an epoxide. So let's go ahead and break that down. Let's put our epoxide here first. Oh, right there, there's our epoxide and our carbon chain. And looking at this epoxide, did we want to attack the most substituted side or the least substituted side? We want to attack the most substituted side. So are we going to use an acid or a base? We're going to use an acid. So are we going to do this? No. We're going to do this. Make sure to put the H plus too. Show it's an acid. Do we need to synthesize that? No, we're good. Yeah, we're allowed cyclohexane or cyclohexanol actually, so we're good there. We don't actually need to synthesize that. Double check though. That's crucial. So if you were to use that on your arrow and you weren't given that as a starting reagent, you would have to go ahead and synthesize that. In this case though, you're given cyclohexanol as a starting product, so you're good to go. So in acidic conditions, that'll go ahead and attack the most substituted carbon. So we know we did this right. How do we make epoxides? What's our go-to reagent? MCPBA. Awesome. So what was there originally? If we use MCPBA on this thing, what did we have in the first place? A double bond, exactly. Moving on. Rocking. All right, forming this double bond. The techniques we have in our pocket are really E2 and acid-catalyzed dehydration. There's a couple more weird exceptions. Those are your main things that you want to use. Let's go ahead and use acid-catalyzed dehydration. I like it. So what are the reagents for acid-catalyzed dehydration? H2SO4 and heat. What do y'all think of this? Is that good or bad? That's not great. It's not great. You would get points off because this would be low yield. And the reason is because the double bond could form here, here, or here. So you're going to get a big mix of products. What could we do to reduce that, to prevent that from happening? Let's put the OH somewhere else. So we could put it here instead. Because remember, it's going to form the most substituted alkene, so that's only going to leave you this. That's by far the higher yield pathway, like by a long shot. You've cut your yield in a third if you go the other way. So she would take points off for that low yield. So keep that in mind as well if you're going to do a dehydration. So we've got this OH here. We need to get rid of this guy right? We're not allowed that, right? So we need to bust that guy off. It's 5 carbons, or what is it? 1, 2, 3, 4 carbons, sorry. 4 carbon piece we need to break off. So what would we maybe use to deal with that? Grignard, right? And we need an alcohol for Grignard. So we're looking good. This is great. So we got back to an alcohol. We're ready to do Grignard. Notice again, our nucleophile attacks that carbon. Where's the OH? The carbon next door. So what was there before? What's at the bottom of our arrow here? An epoxide. If it's one next door, it's an epoxide. If it's right on it, it was a carbonyl. So let's go ahead and do that. I'm going to snake around here because I'm running out of room. We're going to say for Grignards, what do we say after? Then H3O plus. So what you had before, remember, was what? An epoxide? Right, epoxide. So we have this epoxide, and we're going to combine that with a Grignard. Those are a little close. I don't love it, but okay. So looking at our epoxide, do we have a more substituted side? We don't. Both sides are equal in this case. So do we need to worry about acidic basic conditions? No. Reaction will proceed the same way either way. So there's no least or most substituted carbon. So we're good to go. So Grignard would just attack either, and you'd end up with the same product either way. So let's just go ahead and synthesize this Grignard quick. How do we make Grignards? Mg and ether. You can put THF if you want to use a specific one. That gets you back to an alkyl halide, right? Let's double check what we're allowed. Let's go back here. Cyclohexanol and any other alcohols of 4 carbons or less. So we're not going to go back to alkane, are we? That's a critical piece. Don't go back to alkane. Double check, triple check what you're allowed to use. So putting this Br here, and we want to start with alcohols. What do we use here? PBr3. And that's an SN2 reaction. OH there. And we now have a 4-carbon alcohol. We are allowed 4 carbon alcohols. So we're good to go. I'm really running out of room, so I'm going to go ahead and put this over here. Move. So we have our epoxide. How do we make epoxides again? Yep, MCPBA. Meta-chloroproxy benzoic acid. Double bond. What are we allowed to start with again? Cyclohexanol. How do we take an alcohol and form an alkene? Acid catalyzed dehydration, H2SO4 heat. That's not an A, I guess. And can we pick either side in this case? Yes. There's no more or less substituted side. There's no other possibilities. Only one place it can go. And either direction it goes, you'll form the same product. Now we're done. We formed cyclohexanol. Critical takeaway, I think, from this is looking at the position of the alcohol. So look at that alcohol. If it's on the carbon that the nucleophile attacked, it was a carbonyl. If it's next door to where the nucleophile attacked, it was an epoxide. That's the big takeaway. It probably will be your mechanism or your synthesis. Cool. Spec. We are almost out the door. We're good. What is the very first thing you do when you do spec problems? Unsaturation number. That's really where you want to start. What does unsaturation number tell you? It tells you how many double bonds, rings, and that also includes carbonyls. I guess double bonds. I mean carbon-carbon double bonds or carbon-oxygen double bonds. Also rings. So let's do that. Remember the formula is the number of carbons times 2 plus 2. Take that. Subtract the hydrogens and divide all that by 2. We'll talk about what to do with nitrogen, oxygen later. For now, ignore oxygens. You won't see nitrogen, so don't worry about nitrogen yet. All right, so plugging in what we get. So 10 carbons times 2 is 20. Plus 2 is 22. That's how you start. Times 2 plus 2. So 22, and we have 10 hydrogens. 22 minus 10 is how many? 12 divided by 2 is 6. So we have 6 unsaturations. That's a lot. Typically, if you have 4 or more, you will often see a benzene, especially if you have something like 6. Benzene is very common. Let's look at benzene. We said double bonds counted and rings counted. So this benzene counts for 4. 3 double bonds, so 1, 2, 3 unsaturations, and then the closing of the ring counts as the 4th. So having a benzene ring there automatically gives you 4 unsaturations. So if you have 4 or more, benzene is likely, especially if you have 6. Benzene is it's going to be there. The other place to check for benzene would be from 7 to 8 on your proton NMR. If you get these weird squiggly signals with 4H, 5H, something like that, that's your benzene. So we've now confirmed we have benzene in this molecule. So let's go ahead and even just draw that. So that's 4 of our unsaturations, right? How many times, giveaway, how many times is this benzene substituted? 1 time. How do you know? 5H. Yes, so on a completely unsubstituted benzene, pure benzene, there's a hydrogen on each carbon. So 6 total hydrogens. If you have 5H in the integral, that means one of the H's is gone and replaced with something else. So that means there's going to be one thing sticking off of here, right? Nothing else. If you had 4H, 2 things sticking off. For now, don't worry about where. So you can put it at this point wherever you want. We'll get better at spec later in the semester, and you'll be able to see where. But you're not responsible for that yet. But 5H, 1 substitution, we don't need to worry about where. So we know we have a benzene, 5H. So that knocks out 4 of our unsaturations, right? We had 6, so there's 2 more. And remember, rings or double bonds, carbon-carbon double bonds or carbon-oxygen double bonds. So we should be looking now for the presence of alkenes and carbonyls, right? So the place to look for carbonyls is 1700, smack dab on it. It can vary maybe about plus or minus 30 or so. Not much. But so right here with 1682, that's fine. It's right within the range, but it's got to be really, really close. That is a typo. It kind of looks like 8. So this is 1682.14. It does kind of look like an 8, but you can see here is 1700, and it's just below. So it looks like 1882. It's not 1882. It's 1682. Because here's 1600, and then this is 1622. So that's clearly a 6. I think it's just kind of how it copied. That's a 6. Don't worry about it. So looking at this, though, we have a carbon-oxygen double bond, right? So with this really sharp peak, basically right smack dab at 1700, that's going to tell us carbon double bonded to oxygen, right? So we have a carbonyl in this molecule of some kind. That means it could be a ketone, aldehyde, could be an acid. How would we check if it was an acid? Maybe looking at the formula. How would you know it was an acid? Maybe 2 oxygens or more. Could maybe be an acid, and there would be a bunch of other clues. But in this case, since there's only 1 oxygen, it's got to be a ketone or an aldehyde. There's no acid or any of that, since there's no second oxygen. This other signal right here at 1622, what does that tell us? Carbon-carbon double bond, right here. Particularly a conjugated one. So these 2 signals, notice how they're downshifted a little from normal. Normally you'll see this at 1650, and then normally you'll see carbon-carbon double bonds right pretty much smack dab at 1700. They're a little bit further down than normal. What that means is that they're conjugated. And that means that they're next to each other. So the benzene ring, the double bond, that carbonyl is all in one big conjugated system. So that's a clue too, if you see it moving down. If you don't catch that, not a big deal. There's a bunch of other clues that'll help us get to the structure. But that helps. If you can notice that conjugated system is there, you know that all of those are connected to each other, right? That it's all one continuous string of pi orbitals. So that's really all I would get out of your IR. IR, I don't think is that useful compared to proton NMR. You're going to get most of your information from proton NMR. What I like to do is I like to draw a picture above each of my signals about what I think it is. So let's look at this 3H. That's a CH3, right? The other clue you got, it's down here, very far to the right. This is at 2, and that's higher than normal. Normally you'll see CH3 at like 0.9 or something like that. But 3H is almost always CH3, and it's connected to something with how many protons on it? None. And you find that information from the number of peaks. So n plus 1 rule. So we have 1 peak here, right? So what does n equal? 0. 0 plus 1 is 1 peak, right? So the number of peaks, n plus 1, n is 0. So no neighbors. So that means there is nothing, there's no protons on that thing that's next door. So whatever's next door has no protons on it. And then I like to box whatever it is that I'm working with, like whichever signal, like the 3H here, like this CH3 is producing the signal. I put a box around that to say this is the one that's producing that signal. Let's move on over here. We said the 5H was a benzene. This 1H here, it's kind of funky, and it's way down by the benzene. So what do we think that might be? It's hard to know off the top of your head. One place you could check would be the chart. You're given this chart on the exam. I have some little, there's notes here and stuff like that. You won't get any of these, obviously, but you will get this chart, and it has a lot of useful information in it. So let's go ahead and look here. That little 1H signal was between 7 and 8. Let's look here between, like things between 7 and 8. So we know we have an alkene in here, right? So looking at this, so it could be, that looks like something that might match, right? So we have that one hydrogen on there, but it does say 5.2 to 5.7. So that's a little out of range. But what might be shifting this downfield is something electronegative. So it doesn't have to line up. What this means, since it's normally 5.2 to 5.7, is that it's adjacent to something electronegative. But what we can go ahead and do is draw carbon, the double bond, H, and then R, and then carbon with how many hydrogens? So looking at this peak, how many neighbors does it have? No proton neighbors. Yep, so this carbon just has R groups attached. And then this R, so none of these R groups have protons. Isolated, right? One single peak, multiplicity 1, no neighbors. The other reason that it might be down here is, remember, it's conjugated with our benzene ring. So it's very similar to our benzene double bonds, where it's all just kind of circulating and, you know, all the electrons are delocalized. They're just running through the system. So that double bond is going to be similar to our benzene, and that's kind of why it's shifted down there. Let's look at this guy. So we have between 9 and 10. We're not used to seeing things there. Let's go ahead and check our sheet and see what that might be. Aldehyde, 9.5 to 9.6. We know we have a carbon-oxygen double bond. We know we have a ketone, right? Or not a ketone, but a carbonyl. And we see that aldehyde hydrogen right here, right there, that guy, shows up between 9.5 and 9.6. Let's look back here. That's pretty dead on, smack dab. So that is an aldehyde. How many hydrogens are on that carbon? The adjacent carbon, that adjacent R group. None. How do you get that information? Look at the peak. Yep, one peak means how many neighbors? 0, exactly. Yep, so there's no neighbors there. So we've got a really good picture of what's going on here. We see this benzene ring is terminal. We see this has to be terminal. We see this has to be terminal. So there are 3 terminal ends to this thing. So there's like a funky branch point at some point. Looking at this double bond here, we see 3 R groups coming off of it. So we know we have 3 terminal ends, and we know we have a double bond that has 3 R groups. Makes it pretty easy to put the structure together, right? So drawing these pictures really helps a lot. Because see, so you have this double bond, 3 R groups, right? And we know we have 3 terminal groups, right? So let's go ahead and start with our double bond. We know there are 3 R groups on this thing. What we're going to do, we're going to slap them on. Conjugated. Also conjugated. CH3. And there's an H right here. Let's now double check that we did this right. Let's count our carbons. There's 6 in the benzene. 7, 8, 9, 10 carbons I count. Let's go ahead and check. 10 carbons, good. 5 hydrogens on the benzene, so 5, 6, 7, 8, 9, 10. Look back up, 10 hydrogens. Single oxygen. This looks great. We're good to go. Always double check that. That's a way to save some points. We made it, ladies and gents. So, yeah, thank you guys so much. Good luck, for sure. Study hard.
Good job, Chance.
Yeah, it's not in this document. I can go ahead and add it, though, and that way it'll be posted in with the final document. Cool. And if you have other questions, you can just come up and ask us.
Make sure you score that recording.